Operation level concurrent transaction execution for EVM-compatible blockchains. So before we start, let's take a look at the overall blockchain technology stack. A blockchain system is typically composed of two components, the consensus layer and the execution layer. And the execution layer can be further divided into the execution machine and the storage engine, where the execution machine processes transactions and updates blockchain states. So in our work, Parallel EVM, we focus on accelerating the execution machine via fine-grained concurrent transaction execution. So at the core of Ethereum's execution is the Ethereum virtual machine, or EVM. It is a stack-based virtual machine designed to execute smart contracts. For each transaction, the EVM begins execution with an empty stack and memory. The transaction execution updates the Ethereum world state, including account and storage states. To ensure that all nodes in the distributed trustless network agree on the same state view, Ethereum currently uses the sequential execution model. Within each block, transactions are executed one by one, following the preset transaction order. However, this sequential execution model has a major drawback. It completely ignores the potential parallelism offered by all modern multi-core systems. As a result, Ethereum fails to scale, and its execution throughput becomes a bottleneck in current Ethereum ecosystem. To address this issue, many researchers have explored concurrent execution methods to improve throughput. The idea is to speculatively run transactions in parallel and then ensure correctness by enforcing deterministic serializability, which is a concept borrowed from database systems. That is, the results of concurrent execution must be identical to those produced by the serial execution following the preset transaction order. Thus, traditional approaches generally follow a three-step procedure. First, execute all transactions in parallel, treating each as isolated. Then, validate and commit each transaction based on the preset transaction order. If a conflict is detected, the transaction is aborted and re-executed. This ensures equivalence to serial execution. But in practice, things don't work out smoothly, especially in real-world blockchains due to data contention. Let's take Ethereum as an example. The workload exhibits a strong hotspot pattern. A small fraction of smart contracts and storage slots account for the vast majority of function calls and state accesses. This creates a high conflict rate where many transactions operate on the same data, especially on popular smart contracts like WETH. As a result, even though transactions are executed concurrently at first, most of them fail validation and must be rolled back and re-executed serially. The root cause of this inefficiency lies in the granularity of concurrency control used by traditional methods. Most systems adopt a transaction-level conflict resolution strategy. Each transaction is treated as an atomic unit, all or nothing, which means if any part of a transaction conflicts, the entire transaction is aborted and re-executed. This coarse-grained approach leads to unnecessary rollbacks, especially when only a subset of operations within the transaction are actually conflicting. So here's our key insights. While traditional methods treat entire transaction as atomic, but in reality, most conflicts occur at the operation level. Only some operations within a transaction actually conflict. Let's consider a simple example. In transaction 1, A sends 10 tokens to B, and in transaction 2, A sends 10 tokens to C. These two transactions conflict because they both access its balance. But notice that the updates to B and C's balances are independent. They don't conflict at all. And this motivates us to rethink concurrency control at a finer granularity, one that operates at the operation level instead of the transaction level. So based on our insights, we propose a new approach, operational level conflict resolution strategy for concurrent smart contract execution. Instead of aborting and restarting the entire transaction upon detecting a conflict, we identify only the conflicting operations and re-execute them, while preserving the rest of previous work. So back to our previous example, both transaction 1 and 2 concurrently execute. When transaction 2 fails validation because of a conflict on its balance, we only need to re-execute the operation that updates its balance in transaction 2, while the update to C's balance remains correct and does not need any rollback. This fine-grained strategy allows us to retain as much parallelism as possible while still preserving correctness through our partial re-execution. And of course, enabling such operation-level re-execution is not trivial and poses several technical challenges. The first, the EVM is a stack-based virtual machine, and the instructions do not explicitly reveal data dependencies, making it hard to identify which instruction depend on which operations. Second, when re-executing only a subset of operations, we need to reconstruct the exact runtime context, including stack, memory, and persistent storage. Otherwise, the re-execution cannot proceed. Third, we must preserve correctness in the presence of diverging control flow passes, unknown memory accesses, and instructions with dynamic guess codes, which may change depending on the runtime context. To overcome the above challenges, we first introduce the SSA operation log. For every executed instruction, we create its static single assignment form. The SSA representation gives an explicit definition use chain, which helps process dependency tracking. Besides, it also records the inputs, outputs, and the operations that define the inputs, facilitating runtime contexting recovery. Second, we introduce constraint guides. These constraints are synthesized during the initial execution to enforce sensitive conditions remain consistent with the origin execution, such as branch targets and conditions, memory and storage addresses, and the guess codes of the re-executed instructions. During the re-execution phase, we use these guides to ensure correctness. If any of these constraints are violated, we abort the re-execution to prevent any inconsistencies. And together, the SSA operation log and constraint guides enable fine-grained, safe, and efficient partial conflict resolution. So this example shows the corresponding SSA operation log of the transaction 2. Each line represents a generated log. The dotted lines connect dependent instructions. Thus, there exist 3 independent operation groups. Diamonds are synthesized constraints. Transaction 2 conflicts on balance A, causing the storage load instruction as load reading dirty state from account A. Thus, we first identify instructions depend on this dirty read. Using the SSA operation logs definition use chains, we can identify these instructions precisely, which we marked as the orange color. And as shown here, only 5 out of 13 operations are actually affected by the conflict. We then re-execute only these dependent instructions, updating their results while leaving the rest of the transaction untouched. So let's look at the overall system architecture of ParallelEVM. It retains the general structure of optimistic concurrency control, but introduces SSA operation log generation and fine-grained redo strategy. The system works in 4 main phases. The SSA operation logs are recorded in the record phase. In validation phase, we serially verify transactions read side against the latest committed states following the preset transaction order. If a transaction passes validation, it proceeds to commit. Otherwise, it is forwarded to the redo phase. Instead of aborting the whole transaction, we identify and re-execute only conflicting operations using the SSA operation logs. If all constraints are satisfied during redo, the updated execution results is also committed. Otherwise, the transaction is aborted and restarted from scratch. Now let's look at how we generate the SSA operation log in detail. For each executed EVM instruction, we create a corresponding log entry, which is structured and contains 5 fields. First, the incremental log sequence number, or LSN, uniquely identifies each instruction execution. The second is the instruction's OP code, for example, add or sub, and memory load. Third is the operand field records the actual input value used by this operation, and then the result denotes the output value produced by the operation. And finally, the definition field, or def field, tracks the definition operations of each operand. It maintains where each input value comes from. Depending on the source of operand, we handle it in different ways. If the operand is an immediate value or constant value, we simply record a null maker. If the operand comes from a previous operation or a previous instruction, we assign the log sequence number of that operation to the field. And for S-load operations that access persistent and global storage, we log the corresponding storage key to that field. These logs follow from a complete structured trace of the transaction execution, making dependencies between instructions explicit. To track definition operations at runtime, we implement a shadow data structure alongside the EVM. So instead of storing all actual values, the shadow structure stores the log sequence numbers of the instructions that route to each data location. So in other words, for every piece of data, the shadow structure records which instruction produced it. And specifically, we implement the shadow stack and the shadow memory. And let's take the shadow stack as an example. To track where each stack operand comes from, we maintain a shadow stack that mirrors the real EVM stack. And importantly, its operations are completely consistent with the real stack. So for example, if an add instruction pushes a result to the stack, the shadow stack records the log sequence number of that add instruction at the same position. And when the add instruction is executed, it pops 2 operands from the top of the stack. The definitions of these operands are the log sequence numbers stored in the previous top 2 entries of the shadow stack. So in this way, we can accurately track which earlier instructions produced each input and record them as definition fields in the SSA operation logs. And in addition to the shadow stack, we also maintain a shadow memory to track definitions for memory-based operands. The idea is similar. Just like the shadow stack mirrors the EVM stack, the shadow memory mirrors the EVM's linear memory space. For each memory byte, the shadow memory stores a tuple of, first, the log sequence number of the operation that last route to that memory byte, and the offset of the operation result. Even with the precise definition use tracking, there are still cases where data dependencies alone are not enough to guarantee correctness during execution. That's why we should introduce the constraint guides. And specifically, we handle 3 types of constraints. First, for branch-related instructions, we record the expected execution path, and during re-execution, we ensure that the path is not diverged from the original. And for memory or storage operations, we enforce that the re-execution reads and writes to the same locations as before. And this is important to prevent unknown read and writes. Some EVM instructions have dynamic guess codes, which may vary depending on the input values or the runtime context. We record the origin guess codes and ensures that it stays identical during the re-execution. These constraints are act as assertions. If any are violated during redo, the re-execution is aborted and to avoid any inconsistencies. And together with operation logs, constraint guide enables safe and deterministic re-execution. So let's discuss how to identify and re-execute conflicting operations. The process begins during the validation phase, where we first verify each transactions with side against committed states. The sources of conflicts are S-load instructions that read dirty and stale states. Once we identify all conflicting sources, we use the operation logs to trace all operations that depend on them. The re-execution process and the process in the following steps. First, update the result of conflicting S-loads and to reflect the latest committed states. Second, update the operands for each downstream dependent instruction and re-execute each dependent instruction, updating its result. And we should repeat steps 2 and 3 until all affected instructions have been re-executed. We run experiments using historical Ethereum mainnet transactions, and we compare parallel EVM to optimistic concurrent control, two-phase locking, and block STM, which is a state-of-the-art concurrent solution. Parallel EVM achieves over 4 times speed up in standard settings, and furthermore, when combined with state prefetching, the speed up exceeds 7 times. We also evaluate how different factors influence parallel EVM's performance, and specifically, we examine the impact of contention level, block size, and the number of threads. Parallel EVM achieves highest performance for every scenario. And these results confirm that our design is scalable and robust under varying workload conditions. So to summarize, in this work, we first observe that current concurrent control methods in blockchains are coarse-grained and inefficient. Most systems operate on the transaction level and suffers from high abort rates due to hotspot data. Then we propose our parallel EVM, a novel scheme that resolves conflicts at the operation level. By using the static single assignment operation logs, we can precisely identify dependencies among instructions. And we selectively re-execute only the conflicting operations rather than restarting the entire transaction. And finally, parallel EVM achieves remarkable improvements on performance and scalability. And thank you for your listening.